Okay, so good morning, everyone. Start the Thursday morning with a Daniel who will tell us that doubly efficient here.
Great, thanks. So I'm going to talk about doubly efficient private information retrieval and fully homomorphic RAM computation, showing work with Wichs and Ethan Muck. So I'm going to tell you what these things are in some detail in just a little bit. But before I do, let me start with kind of a high level, slightly informal, just motivating example about what this work is really all about before we get into technical details. And the motivating example will come from something we do all the time, just Google search. So here we have a user, she wants to search the internet. Let's say she wants to know what COVID symptoms are. So she asks Google and gets a bunch of search results. And so this talk is about privacy. By having Google see all of our search queries throughout our lives, it really gives Google a very detailed and deeply personal view into our life. And maybe we shouldn't be comfortable with that. So can we do this while having privacy? And so what this would look like is that the user would somehow encrypt the search query before sending it to Google under a key that the user has. And Google doesn't have the key, so they get the encrypted search query. They have no idea what the search term is. But nevertheless, Google can still kind of answer the search query with some encrypted search results without ever learning anything about the user's query. So this sounds magical, but we actually, for the last 15 years, we have a magical tool that solves this problem, fully homomorphic encryption. It exactly lets you do this and enables arbitrary computation over encrypted data. So Google can take the encrypted search query and perform the Google search algorithm under the encryption and produce the encrypted search results without ever learning anything about the query itself. So amazing tool, we should be really happy about it. But I claim there's a major caveat here. There's a major issue with using fully homomorphic encryption. Even if we really optimized the FHE and got it to be like really as efficient as we could dream, it would still not be a good solution to this problem. And the reason is that in order to use fully homomorphic encryption to do this, Google would need to read the entire content of the internet to answer every single search query. And so that's pretty much infeasible. Right? Google can't read the entire internet for every single query. So that's a major caveat here. And the reason for this, the reason that Google has to do this is because fully homomorphic encryption operates in the circuit model of computation. You take the computation, write it down as a circuit. And if you wanted to write down the circuit for Google search, that circuit would be as big as all the data it depends on, which is the entire internet. So it would contain the entire internet inside it. And this is not just some like kind of minor issue with our current solutions to fully homomorphic encryption. This is really baked in to how fully homomorphic encryption works. All it does is you can take two encrypted bits and produce, let's say, the encrypted NAND of the bits, and that's complete for evaluating circuits. So really, like fully homomorphic encryption is tied to the circuit model as it's currently defined. And that's really the point of this work. We're going to take fully homomorphic encryption and port it into the RAM model. Yeah.
Someone who only knows a bit about the FHE, would you need all of the data to also be encrypted with the user's key, or can you somehow do it without being encrypted with the same key?
Are you talking about the
yes,
internet
like
data?
A simple solution.
Yeah.
Can you do the computation even though only the query?
Yes. Yes, you can kind of think of the circuit like thinking of the internet as part of the description of the circuit you're evaluating from the query. So you would like hard code all the internet data into the circuit. Good. And so that's the goal of this work, is to take FHE and port it from the circuit model into the RAM model. I'll define it somewhat generally, like what this means in general later on in the talk. But for now, for the special example of Google search, what that would mean is that Google just would take the internet content and pre-process it into some data structure that it will keep on its side. And then whenever it gets an encrypted search query from a user, it can answer it with encrypted search results just by looking up some small number of locations in the data structure without reading the entire internet.
Yeah, and they already pre-process the internet into specialized data structure.
Excellent. So that's exactly what I was going to say. And already currently, like Google has to build an index of the internet. So they already have some data structure of the internet. So in some sense, this data structure would be specialized. It would be made for answering encrypted queries, not just basic queries. But at a high level, it doesn't look that different from what Google currently does. Like the high level solution concept is really the same. So wouldn't really change kind of the nature of how this works.
And are you thinking this pre-processing is being done for a particular user or a universal pre-processing?
Universal so this pre-processing is done once for everyone, and then any user can come and search the internet, and Google just looks at the tree locations. Yeah, so this pre-processing is completely universal. It's deterministic function, some sort of deterministic thing that Google does. But I'll get into the details. I'll define all these things. So that was the high-level overview. That's kind of, if you want to remember, like a 5-minute summary of what this talk is about, that's it. So now let's actually kind of roll up the sleeves and get technical. Yeah.
So it's also necessary, right? And how this pre-processing?
Yes. We'll get there. Yeah, absolutely. Okay, so we're going to talk. So really, I already told you a little bit about fully homomorphic encryption, the RAM model. That's the main goal of the talk. But I'm going to do a bit of a bait and switch, and most of the talk is actually going to be about a simpler primitive called doubly efficient private information retrieval, or DEPIR. You can think of DEPIR as a special case of RAM-FHE, where the computation is just that the user wants to access a single entry in a database on the server without revealing to the server which entry it is. So it's a special case of RAM-FHE, but it's actually like the heart of RAM-FHE. I mean, the heart of RAM computation is accessing data in a having random access to memory. So once you solve the first problem, it's actually quite easy using our techniques to also then solve the second problem. It's not generic. I don't know how to generically go from the first to the second, but at least with our techniques, it's the first problem is really the heart of the solution.
With strong tools.
With very strong tools, like with obfuscation. Heuristically, yeah.
The station is not like DEPIR.
Yes. Good. Okay. So let me tell you about, let me start with defining this doubly efficient private information retrieval. Let me actually start with basic private information retrieval, which is a problem that's been around since the late 90s. So here we have a user that has an index I, and the user wants to retrieve the ith entry of the database without revealing the index to the server. Okay, so maybe for concreteness, you can think of the server as Netflix as a movie database, and the user wants to watch the ith movie without revealing to Netflix which movie she wants to watch. So there's a trivial solution, which is that
One-bit movie, right?
okay, sure. The alphabet can be bigger.
It's a short.
It's a short problem. All right. So there's a trivial solution to this. What's the trivial solution? Just Netflix like sends the entire movie database to the user and says, okay, pick your movie to watch. But that's not very efficient. Requires downloading everything. And we've known for a long time that using cryptography, most kind of the standard public key cryptomania assumptions that we know of, give us a much better solution, gives us a non-trivial private information retrieval, where in fact you can get very little communication, like polylog n. So the user and the server runs a protocol, and the user learns the ith of the ith location of the database with very small communication without revealing that. But just like before, just like with Google search, the RAM-FHE I was telling you about before, there's a caveat here, which is that although the communication complexity is small, the server has to read the entire database during the protocol. So if the user wants to like watch one movie, Netflix would still have to read the entire movie database to serve that movie to the user. And that makes this kind of inefficient or impractical in many cases. And actually, it's easy to see already in this context that it's inherent. If the server did not read some portion of the database, it would know that the user's index is not in that portion of the data, which would reveal something about the index. So it's actually necessary that the server has to read the entire database, but we want to get around this anyway. So even though it's inherent, we'll try to get around it. And the idea of getting around it, so this is called doubly efficient private information retrieval, to indicate that also the server should be efficient, should not read the entire database. And the idea for how to do this is that the server will pre-process the database ahead of time in an offline phase before any user comes, before anybody wants to read any data. And this pre-processing just converts the database into some static data structure that I'll denote by db tilde. And this is done just once at the very beginning. It's a deterministic function. There's no randomness. There's no secret keys here. It's something the server can do on its own. And this pre-processing can run in linear time, could scan the entire database, maybe even slightly superlinear. And so the data structure size might also be slightly superlinear. But once this is done, once the database is preprocessed, the server now just stores this preprocessed data structure. And then any client can come and want to read the ith location, they can run an efficient protocol where both the communication of the protocol and the server computation is small, only polylogarithmic in the data size. Which means that the server can only read some small number of locations in this preprocessed data structure to run the protocol. Okay, ideally just polylog it. So why is this problem hard? Well, the server only reads a small number of locations in this data structure during the protocol and knows which location it reads. It sees which location it has to access during the protocol. And these locations just don't, there's too few of them, they don't carry information about the entire database. So if the server was unbounded, it could kind of figure out which locations of the original data these blue locations carry information about and learn about the index that the client is querying. Now, the hope is that because the server is computationally bounded, it cannot figure that out. So there's some hope to do this, but this kind of it has a lot of structure and doesn't look like any of the computation assumptions like factoring or LWE that we use in crypto. So it's kind of not clear how you would use standard assumptions to create something with the structure. That's the difficulty of the problem.
Really, the difficulty is that the server is the one who's usually, you have an outside person who's like encrypting. Here, the server is doing it, so he kind of should know where the information is.
Exactly. This is like a totally determined, the preprocessing deterministic function. So the server knows like how the original data maps to this database. It's not clear where to embed some computation assumption to this. So let me tell you a little bit about the prior work on this problem. So this notion of doubly efficient peer was introduced by Wichs and Malkin in 2000, so over 20 years ago. And they had some constructions in the multi-server setting, which I'm not talking about here. In the single server setting, which is the focus of this talk, they really had no idea, and they asked, is this possible? And really at that time, I think the answer could have gone either way. In fact, I think around 2010 or 2011, I spent some time trying to prove a negative result that this is impossible. So it was really unclear which way the answer would go. And that changed in 2017. There was two works that I think finally gave the first evidence that this is likely possible. So what they do, they gave heuristic constructions of a relaxed variant, not quite the variant I told you about, but a relaxed variant that I'll call keyed doubly efficient peer. So what does that mean? So in this variant, the preprocessing is not a deterministic function the server does on its own. It's a secret key. It has secret randomness. It has to be done by some external trusted party. So some external party preprocesses this database with secret randomness and then publishes a public key that clients can use to access the data. Okay, so it's a relaxation, but it still kind of captures the heart of what you want. And they showed how to do this under heuristic assumptions. So security relied on a new assumption over permuted Reed-Muller code, plus an additional heuristic use of virtual black box obfuscation. It was not clear you can do it like under Octo. Okay, so quite strong new assumptions. And so it was open whether you could get rid of either of these. First, construct unkeyed, the basic notion of doubly efficient peer under any assumptions, even heuristically, or construct even the keyed variant under better assumptions. And so in our work, we kind of answer both of these questions. So we get the standard, the original notion of unkeyed doubly efficient peer from standard assumption, namely the ring learning with errors assumption. Let me just say a little about this assumption. So this is fairly well-studied assumptions. It's as hard as finding approximate shortest vectors in ideal lattices in the worst case. And it's the basis of the new NIST standard for the next generation of post-quantum public key crypto. So it's not just like us betting on this assumption, NIST is betting the US economy on this assumption as well. For those who care, we do have some other alternate constructions under related but slightly different assumptions, namely approximate greatest common divisor, approximate GCD, and true and constant rank modulo LWE. The construction actually has a really nice structure. It only consists of 2 rounds. And in the first round, the client can just send the set of indices it wants the server to look up in the data structure. And then the server just looks up with the contents of the data structure at those indices. And in terms of parameters, for any constant epsilon, if we have a database of size capital N, we have a scheme where the preprocessing runs in almost linear time of n to the 1 plus epsilon, and the runtime and communication complexity of the protocol, which is essentially the number of locations in the data structure the server has to look up, is just polylog n. Yes. And furthermore, we can actually also make this construction updatable. If the server wants to update one bit of the database, it can do so by only updating a small number of locations of the data structures of n to the epsilon. So local updates are allowed as well.
Where do you pay for epsilon?
In the polylog, in the exponent of the polylog. Good. So I want to quickly
Just go back to the
Yeah.
slide about the availability. So it's a bit counterintuitive here is that you expect it to be a good error correcting code. And so how do you update the good error correcting code?
Good. So it doesn't have to be a good error. Answer. I'm not going to talk much about it. I'll say a few words on a later slide. So maybe I'll say more than that. Yeah.
How come it doesn't mean that you can just check for each index and to the epsilon places that only they have information about?
Good. So yeah, it is a bit counterintuitive, but essentially means that whatever is updated, whenever you make a query, you always look at those locations. Like that n to epsilon locations that are updated are going to be looked at every time when you ask the next query. And it's going to it uses tools. Okay, I guess I'll say that. But it uses tools from kind of hierarchical ORAM.
Yeah, so it's a different model, right? Now the server is stateful. No, it's not.
The service, of course, it's stateful. It's updating. It has to be stateful, but it has no state beyond the updates. Like, right?
So there is no formal model that is poker, in which this is impossible.
I don't see one that makes sense. I mean, the server has to be stateful. You're right. For updates, it has to be stateful, but that's inherent because it's updating. And yeah, I think it's a natural model. Good. So I want to just quickly compare to some related notions in cryptography that address a similar problem, conceptually similar problem, where you want to access remote data without revealing what you're accessing, namely oblivious RAM and a more recent notion of peer with client-side preprocessing. The main difference for both of these notions and what we do is that in these notions, you need a separate linear time preprocessing of the database for every user that joins the system. Like every time a new user wants to, I don't know, do Google search, Google would need to preprocess the internet for that user. In ORAM, it would have to also store a separate data structure for each user. So we would have to have a separate preprocessed version of the internet for every user that wants to make searches. In peer with client-side preprocessing, it's not the case. It would just store the original data, but it would still have to do the linear time work of preprocessing the internet for that user, and the user would store some hint about this preprocessing. So in contrast, in our notion, there's just a one-time preprocessing that the server does and can be used for all the users, can be reused for everyone in the system. Okay, that's that. So let me, okay, how do we build this notion, this WFH-peer? So let me start with kind of the construction template of how we do this. And the idea is first, we're just going to construct a basic two-round peer, private information retrieval, without preprocessing and without double efficiency. So here the server works in linear time, reads the entire database to answer every query. And well, I'll just give the protocol some names. So the query that the client sends, I'll call it alpha, and the response the server sends, I'll call that beta. And so beta is some function that depends on the database applied to the client's query alpha. This is just without loss of generality. I'm just giving the route some names. And so the second task is going to be, we're just going to take this function f sub db that the server has to compute and try to preprocess it into some data structure that allows the server to compute it very efficiently without reading the entire database. So those are the two steps, but I didn't really tell you anything. This is like, the generic way you would want to do it. It doesn't really tell you a hint about how we do it. And maybe, the reason why this has been hard to achieve in the past is if you think about like the server's computation, this function FDB, it's some complicated cryptographic operations that the server has to do. How do you preprocess this function? It's, I mean, it seems unlikely or hard to imagine that you could preprocess some, this complicated cryptographic operation. So the first step is we're gonna like try to contain step one a little more, try to make it have a nicer format. And in particular, we're gonna construct a peer scheme, a 2-round peer, where the client query consists of some small number of ring elements in some ring R, and the server's response, the server's computation, is just evaluating some low degree multivariate polynomial over the client's ring elements. So now it has some nice algebraic structure. And then we're going to use this beautiful result of Kedlaya and Umans from 2008, which shows that you can pre-process a multivariate polynomial over some rings into some data structure that allows for very fast evaluation. Essentially, to evaluate this polynomial over any future input, you can do much less work than reading all the coefficients of the polynomial. Okay, so the first part, really, there's some limits about what kind of peer we can get, what kind of ring, what kind of polynomials we can get that comes from the cryptography. And the second part, there's a lot of restrictions on what we can pre-process, what kind of polynomials we can pre-process that comes from the algorithm side. So there's an algorithms component and a cryptography component. And a priori, it's not clear that they would like connect up nicely. There's a lot of restrictions from both sides. We found it quite surprising that actually they like meet in the middle and work together.
Flexible than algorithms, I guess.
Actually, yeah, both kind of have a lot of flexibility, but still restricted. But you know, it's kind of surprising they managed to meet in the middle. Yeah.
So in terms of the assumptions that you have, the restrictions on like what those are, mostly is coming from the algorithms part, right? In terms of like, or is it coming from the cryptography?
Well, it's coming from making them meet together, right? So the assumptions are to build this step one, this private information retrieval here that has the right structure and the right kind of parameters to pre-process using this tool here. So you really have to make them meet.
Yeah. Is the size of the process structure also n to the 1 plus epsilon?
Yes. Okay, so let me actually start with the second part, because I think for the cryptographers, if you haven't seen this before, it's maybe more surprising that you can pre-process these polynomials. So I want to actually show you this algorithm. It's incredibly simple. It's in this beautiful paper, but it's kind of used to do more complicated things, and maybe it's hard to like just get this basic algorithm that just solves this basic problem. If you actually look like under the hood, it's quite a simple algorithm. So here's the lemma. We can take an m-variate polynomial over some ring R, where the individual degree of this polynomial is at most d, and we can pre-process it into data structure that allows us to very quickly evaluate the polynomial on any future input. So first, I'll tell you the parameters in a second. First, notice that this polynomial, if it's individual degree d and m-variate, then has d to the m coefficient. So that's the description size. Capital N will be the description size of the polynomial. And here's the parameters. So I don't expect you to read it. I'll simplify it in a sec. But the pre-processing is linear in m, but there's some additional factors here. Maybe the main factor you should notice is m to the m. So this only works when the number of variables is pretty small, actually less than logarithmic. And then the evaluation time. Okay, well, this expression, let's simplify it. So we're going to pick the variables this way. We're going to pick, given like a polynomial length n, which would also be the size of the database later, we're going to set the degree to be like some big polylog in n, log to the c of n. Then we'll set the number of variables so that, you know, this is n. This will be the number of variables. And this will be the size of the ring that will come from the cryptography, 2 to polylog n. For those who I'm hiding some security parameter factors here, just to make it simple.
M is really the standard parameters if you want to use say bit more codes and stuff.
Exactly, right. So this is very similar to read Muller code parameters. And in that case, this pre-processing time becomes just m to the 1 plus epsilon, and this evaluation time becomes polylog n. So this is the set of parameters you can keep in mind. Okay, so let me prove, and I should say this doesn't work generally for all rings, but it works for some nice rings. Namely, it works for ZQ, it works for polynomial rings, even multivariate polynomial rings. And actually, this will be kind of the rings we'll need to get from LWE. Okay, so I'm not going to prove it for general rings, but I'll show you the proof for just ZQ. Okay. So maybe to get some intuition, what are two ways of evaluating the polynomial over ZQ? One is to just keep the polynomial and then you give me the input, I'll just like read all the coefficients and evaluate in a naive way. Another way of pre-processing it is like I could just take every possible input and write down the value of the polynomial, but that'll be like q to the m size data structure, which is way too big. We're thinking q here is already being super polynomial. Okay, so we want to do something in between, something that has like small data structure plus fast evaluation. So the first step is actually to make our life harder. Instead of thinking of this function as a polynomial over ZQ, we're just going to think of doing the computation over the integers without reducing mod Q. Okay, but we'll still think that the coefficients and inputs are in this range 0 to Q minus 1, so they're relatively small. And then we can bound the output size of this polynomial by this capital M, which is 2 to the power log n. So the output doesn't get too crazy because it's low degree, few variables. So this is this as an integer, the output is not too big. And now we're going to use the Chinese remainder theorem.
So Q is to the power log side.
Yeah. Q is like slightly super polynomial. There's going to be a security parameter in there. And so now we're going to, this is the main idea is to use Chinese remainder theorem. So instead of evaluating the polynomial over the integer, it suffices to evaluate it modulo a bunch of small primes whose product is bigger than the integer output of the polynomial.
Evaluated on all points.
And so we're going to just take all the smallest primes, the first.
Then the evaluation is fully.
Good. Yeah. So we're going to take, well, I'll tell you in a second. Yeah. So we're going to take all the smallest primes less than 16 log m, and it turns out that we take the product, it's bigger than m. So we take a small number of primes, and they're relatively small. Each one of these primes less than 16 log m.
This question, I mean, it's a very natural idea. Is this going to be some data structure before the Chinese remainder theory?
I don't know. Okay. So now we just need to evaluate this polynomial modulo each of the small primes. So what do? We reduce the problem of evaluating the polynomial mod Q to evaluating a bunch of polynomials modulo much smaller primes. We reduce from Q to, which is like the super polynomial, to Z to PI, which is polylog. If this is too big, which actually for us it will be, you can recurse again to make the primes even smaller. Okay, but now once the primes are really small, we can just pre-process these polynomials by just evaluating them at all possible points, all p to the m points for whatever the small primes p is, and this will be poly n. And if you do the parameters carefully, it's really just n to the 1 plus epsilon. Okay, and so then the evaluation is just to look up these values in each of the tables. So look up the value of the polynomial modulo of each of the small primes pi, and then reconstruct using Chinese remainder. That's the entire idea. It's extremely simple. Yes.
When you are doing all these things, small primes, you can also reduce the degree, right?
Well, right. The degree is actually much smaller already than the primes, but yeah. Yeah. You're right. The degree is never bigger than the primes, but yeah.
Recursing makes sense. I mean, you're going to have the same primes show up again and again, but they're in like a different context.
Right. So you
mod one prime and then mod another prime, and
so you don't need to build more tables, but you will need to do the work of like first reconstructing mod the like intermediate level primes, and then using Chinese remainder to reconstruct mod Q. So we just need like one recursive call, 2 levels of recursion.
So you convert from like one polynomial to log in many polynomials, mod like smaller primes, then you ignore these smaller primes again, but they're going to have smaller coefficients if that matters or not. And then each of them also sort of blows up to log something smaller. So you get like log n times log something smaller total number of things, and for each one of them you preprocess. Right?
Exactly. Yeah. Great.
so as you go down, sort of the field size and working on is smaller than degree overall across the board.
Sometimes it will be.
Yeah. Yeah. So the field size goes down. Yeah. At some point, it'll be if the primes are very small, then the degree you can kind of ignore it. But yeah.
But is there like not that it matters, like an optimal point, like how small can you make them if you, right? Because there's a trade-off, right?
Right. So this one level of recursion it turns out to be the best. One thing is that at each recursive call, you like make the prime smaller, but then you blow them up by doing this trick. So here the m gets bigger. So it actually doesn't make sense to do more than one level. Okay, so
Just because if there are extension fields, can use multiplication embeddings to do it with other.
so that's how you get more complicated rings. And for example, you can do polynomial rings with this, which is what we'll actually need.
Better parameters actually, right?
So
you cannot get better parameters, like CRT is wasteful, and if
Yeah.
you can get constant.
there are some tricks you can play to optimize this. Let me.
But just again, you need it to be over like a big characteristic. You cannot do say F2 extensions, right? In the process.
Right. So this, here. No, you can because we will actually do it over polynomial rings. We'll do it over. Yeah.
But
you don't need characteristic. There's no restriction on the characteristic.
Okay. So even characteristic. So even this data structure.
I think so. Yeah.
This one or a different instruction.
But I didn't tell you how to extend from ZQ to polynomial rings, but yeah, you can do it.
But Johan is not going to gain what he thinks that he's going to gain.
Yeah, I'm not. Okay, so I'm not trying to optimize here, but like you can do it for these other rings as well. It's kind of similar parameters.
So just checking once Q can be characteristic too.
Yes, I don't care. Yeah, Q can be an integer. Yeah, it doesn't have to be prime. Okay, so good. So that was the pre-processing. So now let's talk about how to construct this basic peer that allows you where the service computation is just evaluating a polynomial over some nice ring. So the idea that we'll use is to actually just build maybe the most intuitive kind of private information retrieval from somewhat homomorphic encryption. Somewhat homomorphic encryption means you can compute some restricted functions, not all functions over the encrypted data. Namely, we'll want ones where you can compute low-degree polynomials. So here's the idea. Let's take the index that the user has and write it down in some base D, which will set to be prime, and it'll correspond also to the degree that we saw in the previous slide. So some fairly small base. And let these just be the digits in this base. So I'm just writing down the index I. And if I do that, you can think of the function that maps this index to the ith location of the database. You can actually just interpolate a low degree invariant polynomial that computes this function. So you can just write down the polynomial. Okay, so now, okay, so this polynomial is individual degree at most D. Well, it's a polynomial over ZD, so degree doesn't need to be more than D. And the total degree is D times number of variables. Okay, and so the client is just going to choose a secret key and encrypt all of these digits of the index using some somewhat homomorphic encryption scheme. And the server has to just homomorphically evaluate this polynomial over the ciphertext. That's the server computation. Okay, and then the client decrypts and gets the right value. So are we done? Can we apply the pre-processing to this construction? Well, not really. The problem is that the service computation is not evaluating the polynomial of DB. It's homomorphically evaluating the polynomial of DB over encrypted data. And if you look at kind of modern homomorphic encryption scheme, the evaluation does a lot of complicated things. It's not just polynomial evaluation.
And in the multi-server setting, why doesn't it work there? So in the multi-server setting, this data structure is not used to.
I didn't say that, but I think it just doesn't give you better parameters than what we know already with read null codes. That's all I meant. Yeah. Okay. So right. So the server has to homomorphically evaluate this polynomial, and who knows what the homomorphic evaluation looks like. But actually, it turns out if you kind of look at nice, somewhat homomorphic encryption scheme, actually not the modern ones, but you kind of take away all the optimizations that modern schemes do to become fully homomorphic and go to the, go back in time and look at the early homomorphic encryption schemes. They actually have a nice structure that where the eval would just be polynomial. In fact, it would just be evaluating the same polynomial of DB over the ciphertext. So we give this a name. We call this type of homomorphic encryption algebraic somewhat homomorphic encryption. kind of the platonic ideal of what a homomorphic encryption should look like. Like if you encrypt, so the plaintext is some space ZD. If you encrypt messages in the plaintext space, you'll get ciphertexts which live in some ring R. And then if you add up the ciphertext, you get an encryption of the sum of the messages. If you multiply ciphertext, you get an encryption of the product. There's some noise, so you cannot do it too often, but as long as you do like few enough operations, this works. And so if F is some polynomial over ZD and the total degree is not too big, then by just evaluating the same polynomial over the ciphertext, you have to lift it to the ring R appropriately, but by just like lifting the polynomial to the bigger ring and then evaluating over the ciphertext, you get an encryption of the output of the polynomial on the plaintext. Okay, and so I said there's some noise and you can't do it too often, but essentially you can set the parameters such that if your total degree of the polynomial is capital D, then the ciphertext size and the encryption and decryption runtime are just poly in D. And our capital D is going to be small polylog n. So. Okay, and so it turns out you can get this type of algebraic somewhat homomorphic encryption by making fairly light modifications to prior somewhat homomorphic encryption schemes. For example, the Brackersky-Mikutana scheme from ring LWE gives you this, or you can use N-true or approximate GCD. And so I'm not going to show it to you, but this is how we get the basic tool that we can preprocess.
So is the point just that the noise doesn't become so big because you have a bound on the degree and the ring is much larger?
Yes. Yeah. So that right. So the ring kind of will grow with the noise, but our polynomials are fairly low degree polylog n. In fact, you could have handled like bigger degree, but just the noise would grow. So we don't even need to use it. We need to use these schemes for a very, very small degree.
To get a subconstant epsilon.
You can, yeah. Yeah, so you can extend it to get like n to the 1 plus the low 1 at a cost of having bigger than slightly bigger than polylog n on my time. Okay, so just to put it all together, so then that gives us the entire scheme. We're gonna first use this basic peer from somewhat homomorphic, from this algebraic somewhat homomorphic encryption, and then we notice that if we do that, then this the computation server does is just evaluating the same polynomial over the ciphertext, over the ring elements that the client sends. So now the scheme has the right structure, and we're just going to take this polynomial and preprocess it with Kedlaya and Umans, and that's the entire scheme. So yeah, let me mention about updatable DEPIR. So in updatable DEPIR, the server can update individual bits of the database and correspondingly update the preprocessed data structure in sublinear time. We get into the epsilon. Our basic construction is very much non-locally updatable. If you look at this Kedlaya and Umans construction, every bit of the data structure depends on every bit of the database, but we can make it updatable using ideas from hierarchical ORAM. Maybe if there's extra time in the end, I have some slides, I can show them to you, but I'm going to skip that for now. Yeah.
You can also extend the database.
Yeah, you can also extend the database. You can add bits or modify bits of the database as well. Yeah. Good. And this is actually generic. You can take any doubly efficient peer and convert it into an updatable one, as long as the preprocessing time is small. So the update time will depend on the preprocessing time. Our preprocessing time was n to the 1 plus epsilon, and that gives us the update time of n to the epsilon. So here we really need to make sure like the preprocessing time is, for example, less than n squared. Otherwise, you don't get anything.
It's in the same strict order with multiple users.
Yeah. There's no secret state. There's not. The update is completely like deterministic. But the data structure, for example, depends on what order things were updated. It's not like I cannot map. It doesn't depend just on the contents of the database, but also in which order it was.
It's not history independent.
It's not history independent, right?
Just ensuring like the size of the database will change. It's
you can do that as well. Yeah, you can add bits.
It's not editing; it can append it as well.
You can append as well. Yeah.
So you can sort of start from an empty database.
Yeah.
It always puts tons of zeros.
Yeah, but you don't need to know the size ahead of time. Yeah. Good. Okay, so now I want to tell you a little bit about how to go from this doubly efficient private information retrieval to fully homomorphic encryption in the RAM model. So first, let me tell you what the problem setting is. So here we have a server that has some arbitrary value y. You can think of it as a big database. Maybe it's not big, maybe it's small. And we have a client that has a private input X, and we want the client, the user, to learn f of xy without revealing X to the server. So X is the thing we're trying to keep hidden. So for example, you can think of this as Google search, where Y is the internet and X is the query. Or you can think of it even as some outsourcing computation. Maybe Y is empty and F is just some very complicated computation the client wants the server to perform on its input X. So there's a trivial solution, which is the server sends Y to the client and tells the client to compute f of xy themselves. We don't like that for two reasons. Maybe Y is too big, so we don't want to send Y to the client. We want to save on the communication complexity. But also F may be very expensive to compute, even if Y is small or Y is empty. We don't want to use the solution because we want the server to do the work of computing F, not the client. Okay, so this is the problem that fully homomorphic encryption solves. So in fully homomorphic encryption, the client just encrypts the input X, sends it to the server, and the server builds a circuit for the function F with Y hard-coded inside, and just homomorphically evaluates the server over the client ciphertext to create an encryption CP star of the output, and then the client just decrypts the ciphertext and C of X, which is just f of xy. Okay, so this is fully homomorphic encryption. And in terms of communication time and the client computation, the client is very happy. It pays just kind of linear in the input size and linear in the output size, which is like the best possible. But the server's runtime is proportional to the circuit size, it's linear in the circuit size, which again, we saw is generally not good, right? For example, in terms of Google search, that would be the size of the entire internet. At least it's linear in the size of Y. So this is something we want to fix. And here we have constructions from nice assumptions like learning with errors or circular security if you want to get the full notion of fully homomorphic. Okay, so to port FHE to the RAM model, kind of everywhere we had circuit, just change it to RAM program. Okay, so now we assume we have some RAM program P for this function F, and we'll need to know some upper bound on the runtime of this RAM program because the server knows how long it runs. So let's say we have some upper bound on the runtime, which we'll call capital T. And so now we want the server's runtime during this computation. The server will homomorphically evaluate this RAM program over the encrypted input X from the client and this data Y, and we want the server's runtime to be just O of T, proportional to RAM runtime. So
is it inherent? Like, can I have input specific running time, or I have to run in time T?
Oh, well, the server would learn how long it runs in. So we have input specific.
It can learn it. I mean, that's not a problem. But can it, like, let's say that some computation takes 5 steps and some takes 5,000 and 5,000
Yeah.
upper bound. Do I need to run in 5,000?
You need to set an upper bound ahead of time. So maybe you could try, like, if you have back and forth communication, you can do better, but with just this, you would need to know upper bound ahead of time. You could try running for 2 steps, sending back to the client and ask, am I done yet? The client will say no. You try again for 4 steps, 8 steps, 16, you know, so you can do that. But if it's not interactive, then we don't actually know how to get it specific.
Or you can just give all power to the tool.
Right, but then the client has to tell the server when to stop, right? Yeah.
So in the setting, you can think of T as much smaller than that of Y, and RM and F is like a symmetry.
Say it again.
You can think of T as much smaller than that of Y.
Yeah. Yeah, exactly. RAM pro. So you can do binary search, for example. Yes, yes. So I want T can be much smaller than this is the RAM model. So yeah, T can be much smaller than 1. Good. So, but this notion, okay, I fooled you. This is impossible for the same reason double efficient P was impossible, because the server sees which locations of Y it touches. It would learn something about the computation, which would reveal something about X. So to fix that, we again need to add preprocessing. So before this computation starts, the server has to preprocess this public input Y into some data structure Y tilde, and then it will use this data structure Y tilde to execute the computation.
If you have programs that write to the memory.
Yes. Good. So wait one slide. So and the preprocessing time ideally would be just linear in Y. Okay, we don't quite get this. We get some 1 plus epsilon factors everywhere. That's okay. So yeah, to answer Omer's question, so I'm thinking of the RAM program P as having RAM access to everything. you can have RAM access to the input Y, which is kind of useful for, let's say, Google search, right? So there X is small, but you don't want to read the entire internet. But I'm also allowing the program to have RAM access to the input X. It doesn't have to do linear scan. So maybe X is an encrypted database and you want to do some queries over this encrypted database that the client outsources to the server. And in addition, the program P could have some additional read-write memory. So this would be useful if like Y is empty and you want to just outsource RAM computation. In general, to convert from RAM to circuit, you have to pay at least linear input size plus quadratic in the runtime. So here you would avoid this quadratic cost. Okay, so we're allowing RAM access to everything.
The persistency of the writes, like if I want to run 2 programs.
Yeah, so we have all kinds of extensions. You can you can do multi-hop, multi-input. So for example, like you can take the outputs of some computation, use it as inputs to future computation. Pretty much everything you can think of is allowed.
So does that give you like a generic solution for the updatable, doubly efficient peer if you allowed write?
Yes, but this uses that to solve the problem. So, right. You need updatable. We use updatable to solve this. Okay, so let me just say about prior work. So in a paper from 2019, we gave the first evidence that this type of RAM-FHE is possible. Actually, we constructed a slightly weaker variant of RAM-FHE. There was no server input Y, which is RAM access to the encrypted data X. So it didn't, for example, allow this like Google search application, but we did it from keyed doubly efficient peer. So keyed doubly efficient peer already uses VBB obfuscation inside, at least at that time. That's the only construction we had. But that wasn't enough. We needed to like use additional VBB obfuscation to then generically convert from DEPIR to this notion. So in this work, we just show that how to do this from ring LWE, well, plus circular security, just because even standards FHE in the circuit model needs circular security. If you don't have circular security, you get something weak or some leveled notion of RAM. Okay, so I said that we want to do this for programs that have RAM access to everything, X, Y, read, write memory. I want to show you a simpler case where the program has only RAM access to the public input Y, but not to X or to any additional read, write memory. Okay, so here's how I want to think of the computation. I'm thinking about it as a bunch of CPU steps. Each CPU has some fairly small like circuit description with some small amount of registers. Initially, the input X is going to be just written on the registers. And each step of the computation like evaluates this kind of one CPU step circuit, updates the state, the registers, and asks to read an index in the data Y. And then on the next step, you magically get the ith bit of the data as an input to the next circuit. So this is just a generic way of writing the RAM computation as a sequence of these small circuit steps. Okay, so the idea is let's use circuit FHE to do the computation. So first, we're going to encrypt X under just a FHE circuit FHE scheme. And then we're going to evaluate these CPU circuits one by one. So when you evaluate this first CPU circuit, you get an encryption of the state plus an encryption of the index that you want to look up in the database. So now in the next step, I want to get an FHE encryption of the value in the memory or in the data Y at that index. But how do I do that? So how do we access Y in this computation? So it seems clear we should somehow use doubly efficient peer. That's the tool we have at our disposal. We need to hide this location I, but still access the ith location of the database. But who makes the peer queries? I mean, there's no client to make these queries. There's just this computation and the server's running on its side. And so the main idea is that actually our DEPIR scheme has a nice structure where we can nicely convert between FHE ciphertext and DEPIR queries and DEPIR answers back to FHE ciphertext. So kind of this encryption of I that we get during the computation, we can actually translate it into a DEPIR query for I, answer it using the DEPIR scheme, and then translate the answer back into an FHE ciphertext that we can then continue running the computation. And the idea is that actually we can build an encryption scheme that's the best of both worlds. It's simultaneously an algebraic somewhat homomorphic encryption scheme, which is the encryption scheme we use to make peer queries, the DEPIR queries, and an FHE that lets you compute arbitrary circuits. And they get kind of the best advantages in both worlds. So as an ASHE scheme, if you want to evaluate low degree polynomials, which is what we needed for the DEPIR queries, you can do this with nice algebraic structure. You just evaluate the polynomial on the ciphertext. You don't need to do anything complicated. But this only lets you evaluate low degree polynomials, not much. But then you can also use it as an FHE where you evaluate arbitrary circuits. But this doesn't. This uses like crazy, does all kinds of non-algebraic stuff, uses bit decomposition. So this doesn't have any nice structure, but you can do it. And moreover, you can go back and forth between these. So if you get an output of the FHE, you can translate it back into the ASHE, and you can think of an ASHE ciphertext and translate it back into FHE.
Translate without knowing the secret key.
Without knowing the secret key, yeah, you can just translate back and forth between these two schemes.
So can you do it generically?
So you can translate to FHE generically, but translating from FHE to ASHE, you need to evaluate the decryption. So we actually by using a careful FHE, it's actually the FHE ciphertext are already ASHE ciphertext, so makes it nice. It's not completely generic, but close enough.
So wait, in your scheme, is there actually a switch, or is the ciphertext just like, is the transformation doing something, or it's identical?
It's doing something in one direction. So when you translate from ASHE to FHE, like after ASHE, the ciphertext looks quite different. And then to translate to FHE, you need to do some kind of bootstrapping, but then the FHE to ASHE, not to do.
So it's not the same decryption algorithm, two different decryption algorithms.
Well, you can always translate to one of these two and have that be the decryption algorithm. That doesn't really matter. Yeah. So it's kind of one scheme, but I think of it as one scheme that lets you do both types of operations, like low degree polynomials very easily by a very nice homomorphic evaluation procedure, or general circuits by a non-nice homomorphic procedure.
I think that they used in like these sort of practical-ish FHE, like TFHE, right? This is sort of the sort of tricks that.
I think so. Yeah. This is like this type of idea that you can. Switching between FHE encryptions is something that's like been done a lot in the past. That's what we do. So we can do this from ring LWE or does assumptions plus circuit security. So then the whole evaluation has this nice structure where you just start with the encryption of X, kind of run the computation, get the FHE encryption. So everything's happening under FHE encryption, get the encrypted index and the next state. Then you translate this encrypted index into an ASHE encryption of the index, but that's just a DEPIR query for the index. So now use the DEPIR to answer it and translate that into an FHE encryption of the output, and then continue the computation. So that's what gives you RAM-FHE. Okay, this only gave you this restricted notion where you only had RAM access to Y, but not to X, and there was no read-write memory. To get random access to X, it's actually very similar. It's quite easy. You can do the same thing. The idea is that when the client's encrypted X, the client already has to scan all of X in linear time to encrypt it. It's also going to apply this DEPIR preprocessing of X to allow RAM access to X. So that's fairly easy to do. Random access memory is a little more tricky, but we're essentially going to use some sort of an updatable DEPIR to keep track of working memory during the computation. So, well, updatable DEPIR was talking about public memory. So here we're going to need to like use an encrypted version of memory with updatable DEPIR to handle this, but it can be done. Okay, so that's pretty much what I wanted to say. Let me just conclude. So we construct both DEPIR and FHE for RAMs from ring LWE, and there's lots of nice open questions left. So for example, can we do it from plain LWE? Pretty much everything in the past we've had from ring LWE, like within less than a year, we've had a way of doing it from plain LWE. So clock is ticking. Let's do it for RAM-FHE and DEPIR.
So here it seems like the main hurdle is the algorithm thing, right?
Yeah, right. So there seems to be the difficulty is that the algorithm works only for specific rings and requires a lot of structure. So seems to be a little harder,
Seems
but
like that's the thing to solve. I mean, if you
that's right. So for example, if you had a way of pre-processing polynomials over matrices, you would be able to solve this problem nicely, but I don't know how to do that. The other question is practical efficiency. This construction doesn't use like any heavy handlers. There's no obfuscation. There's nothing insane going on here. But still, I think practically it'd be quite inefficient if you like did everything naively the way I described.
Are they going to kill you? Or
That's yeah, it's kind of the combination of everything. It's the parameters you get from FHE combined with the pre-processing that's going to yeah, exactly. So I think, but I think there's a lot of room for optimization. There's a lot of flexibility in the algorithm, both and in optimizing FHE schemes you use. So I think there's a lot of hope here to actually make this practically efficient.
Do you have an idea for a heuristic, any heuristic instruction?
No, actually, I don't. Yeah, we don't know the heuristics yet.
Just in terms of heuristic choice of parameters, some gap between the heuristic choice of parameters.
No, even if you use the best, like the you know, we kind of know about
loss because of probable security.
I don't think so. No. I mean, people have instantiated FHE with the most aggressive parameters already, so we can just take that aggressive choice. But it's more about the pre-processing and the polynomials. Yeah, I think there's a lot of room for improvement. And there are a lot of obvious applications. You know, anywhere you want to use FHE or PIR, you can now replace this. But I think it'd be interesting also to find kind of applications for that field. It's a new primitive, and I think it should have other uses that that are not the obvious uses of these tools. Thank you.
So in the doubly efficient peer, you translate each database query to polylogarithmic queries to the preprocess database, right? They're like a lower bound.
Oh, that good question. I would imagine it should be at least security. So we have everywhere I said polylog n, there's security parameter factors, so it should be security parameter. There should be a secure parameter in there. That should be easy.
Should be distinguishability between this distribution over
yeah. You need to have a high entropy of like where a specific index, how many different queries there are for one index. So you need at least.
Questions?
Yeah, actually, so maybe you said I missed it. Where do you use the sort of ORAM inspired techniques? This is to do the write in a doubly efficient peer.
Yeah.
Yeah.
Yeah. So I mean, let's see. I have some slides on it, but
this
I
is
can.
not in the. It's not in the sort of going from doubly efficient peer to the.
No, it's still in the doubly efficient peer setting. So essentially, like you keep the idea is you'll like store. Your data structure consists of many levels. Each one is preprocessed with DEPIR. Whenever you write to the top level, preprocess it, and you somehow every once in a while you merge the top bunch of levels and re-preprocess it. So everything, the server is still deterministic. Every time it's right, it's completely deterministic, but the data structure is now history dependent. Where the data resides on which level depends on when it was written.
So you don't need like the amortized, like the way they should. Well, what kind of ORAM? Is it like a Goldreich-Ostrowski type?
Yeah, it's a hierarchical. It's based on the hierarchical. It's not. I'm not using the ORAM as the black box. It's based on the idea.
I understand.
Yeah,
but the query time, the query time is going to be sort of
the update. The query time is the same. You actually query every level with DEPIR. So the query time is just like logarithmically bigger than the original. But the update time depends on the pre-processing. So every bunch of times I merge a bunch of levels and pre-process. But
so the update time is amortized, or it's
good. It's amortized in the basic scheme, but you can de-amortize it. Like there's standard tricks.
I wasn't going to ask, but since I saw the slide,
yeah, there's standard tricks to de-amortize.
Any more questions? Okay, thank you.
Break, we can be here at 10:30.